Hello. So today let's discuss a little bit on regularization in neural networks. Okay, we have already discussed. So today we'll discuss regularization, uh, regularization in neural networks. Okay. So we have already discussed the regularization in logistic networks in lecture number 12. Okay, so you can go back to the video of lecture number 12, and there you can see how we have discussed the regularization in terms of linear regression and logistic regression. As neural networks are basically composed of logistic units, their regularization is very similar to the regularization of logistic regression. So, for example, a logistic regression unit is can be given something like this. So, this is suppose a logistic regression unit, and this is the h of this is the hypothesis function output. So, you have in neural networks, what happens is we modify the logistic regression to have a threshold of zero point 0.5 within it. Okay, 0.5 within it, but like this neural network basically has a value of zero point 0.5. This neural network will have a model of 1 plus e to the power minus z. Okay. 1 by 1 plus e to the power minus z is the uh, model of this logistic regression h of z is equal to. So in this neural network, for it to have multiple or different threshold points, we need to add a bias unit, which is this, which is a fixed one, and the bias unit is basically controlled. The bias value is controlled by the theta zero value. Then we have inputs, say x1, x2, x3. So these are your inputs, and these inputs are again fed here with a with the theta values theta 1, theta 2, and theta 3. Okay, so these are the weight values for this. So overall, thus h of theta x vector would be given by 1 by 1 plus e to the power minus theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3. Okay, so here theta 0 can control whether whether this logistic regression will have a uh, 0 0.5 will basically transit between 0 to 1 at this point, or it will transit at this point, or it will transit at this point. Okay, so depending on what the theta 0 value is, you can change where this transition will occur from 0 to 1. Okay, and theta 1, theta 2, theta 3, this gives the basically this determines the plane, okay, at which this transition occurs. You go back to the logistic regression if you have doubts on how this thing works. Okay, but this is the formula for a logistic regression unit. Okay, now the loss function for a logistic regression unit was given by loss function, or the error function was given by j of theta is equal to 1 by 2m summation I is equal to 1 to m um, y of I log of h of theta x I x vector I basically here, and yi basically is this one. Yi is whatever is given. Y is the given value, and h of theta x is the predicted value, and you are basically comparing these two. So you can have multiple inputs in this. So you can have x1, x2, x3, and y, and you can have multiple rows. This row number is number of rows are m, so that's what goes here, 1 by 2m. Okay, 1 by 2m, and here you have the row number is ith row. So you are going row by row and checking what is the error using the stochastic using the logarithmic error function. So this is given by yi log h of theta xi minus 1 minus yi log of 1 minus h of theta xi. Okay, Okay, so this is the normal error function. Now if we have when we regularize, what we want is we want all the theta values, theta 1, theta 2, theta 3, all these values to be as small as possible. Okay, we don't regularize the bias function, but the bias value. The biasing weight is not regularized, only the weights which are corresponding to the inputs are regularized. Regularization means we try to minimize the number or minimize the value of these parameters. Okay? So for that, what we do is we to the error function we add plus lambda by 2 1 summation. We want so summation j is equal to 1 to uh, 1 to n, where n is the number of parameters. Okay, so here n is, so here n is 3. Okay, 1 2 3. So here it will be lambda by 2m summation j equal to 1 to n theta I square. Okay, so note here that we do not regularize the bias term. So this is the overall function, which is a regularized logistic regression error function. Okay, so we have already discussed how we go about calculating the gradient of this, and by calculating the gradient of this we can then do the gradient descent and find out the optimal values. Now when we come to neural networks, what happens is neural network is a network of many logistic regression units, although they can have different activation functions, but the basic network is a network of multiple a large number of logistic regression units, all connected with each other layer by layer. Okay, so say neural network consists of say a neural network consists of multiple layers with each layer having an associated weight matrix, associated weight matrix, capital theta I, and bias matrix, capital BI, where I denotes the layer number. I here denotes the layer number. Okay, so the loss function would be given by, so the loss function here can be represented as j of theta I comma pi, or sorry, let's start with theta 1 comma b1, theta 2 comma b2. So these are complete vectors. Okay, so these are complete vectors. Theta, they are complete vectors, so I'm not writing them here, but these are complete vectors, layer by layer vectors. Theta 2 vector, b2 vector, dot 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 up to theta l comma b l vector. So this is the overall representation. This is a functional representation of the error function for the full neural network. This we have already represented. You go back to lecture number 15. Okay, lecture number 15. In that we have really delved into how to get a error function and how to do backpropagation. Only after you have understood lecture number 15, these things will make sense to you. So this will be given by 1 by m summation I is equal to 1 to m. So this is the loss function This is the representation of log function. Y hat I is the output predicted by the neural network, comma yi, which is the given output. So this loss function we have already calculated or found out. We have hypothesized this loss function using the standard. This hypothesis, this loss function has been represented in lecture number 15. You go back there, and you'll be able to figure out. But in lecture number 15, I have not summed it over all the rows of inputs, which is very straightforward if you have solved assignment number 7. Assignment number 7. Okay. In assignment number 7, we have done the loss function as well as summed over all the rows of the MNIST dataset, 60,000 rows in MNIST dataset. Okay, so this is the representation of say the loss function. Just a symbolic representation of the loss function. To this, to regularize, we need to we need to do the L2 norm, which is given by lambda by 2m summation I is equal to summation g is equal to 1 to L. Okay, this is called as the L2 norm theta, capital theta L, capital theta L square. Okay, for all the layers. So for all the layers, for every layer we have a theta matrix which transforms the previous layer outputs to the next layer outputs. For every layer, the theta, for every theta matrix we calculate the L2 norm, which is basically given by which is basically the sum of squares of all the elements in the matrix. Okay, where L2 norm of the theta matrix is given by summation over all elements of the theta ij. Let's make this a small theta ij on the lth layer square. Okay, so what I basically mean is suppose this is your theta matrix, theta 0 0, theta 0 1, theta 0 2, dot dot up to this is theta 1 0, something of this sort. This is there up to theta, suppose mn, something like this. So what I mean by this formula is that you square all of these, and sum all of these, and you get one single number. Okay, and that single number goes here. That is your L2 norm for that matrix. Okay, so every layer has a theta matrix, and there is a bias matrix. Actually, we combine the biases and the thetas together, theta matrix together by putting by putting bias values here. Okay, p0, p1, p2. But by appending the bias values, we whenever there is operation, we append the bias values, okay, to the theta matrix. But what we need to do while calculating the L2 norm is do not square the biases. Okay, only square the theta values and then calculate the L2 norm. Okay, so that's why the bias values are left alone during regularization, just like the way you used to do in the logistic regression case. So once this is done, then you can, so once this part is all done, then you can calculate, you can calculate sorry. Once this is all done, you can calculate dou j by dou theta ij for any theta ijl, which is the change in loss function with respect to by changing a particular value of theta. Okay, there are multiple theta values which are which are there within every layer, and there are multiple layers. Okay, so this is the a particular theta value at the ijth location in the lth layer. Okay, so we have already found out in lecture number 15 that how do we do it from uh, back propagation. Okay, so from back propagation, you can find out dj by dou j by dou theta ij l. In addition to this, you will have another derivative which will come from this. Okay, so this derivative will come, which will be lambda by square value of lambda by square value of a particular theta ij. So this will become lambda by m and theta ij l. So basically this will be this is the sum of all the theta ij. So if you take derivative of theta ij, all will come out and the same theta ij. So for any particular theta ij, you will have one additional term, okay, which is lambda by m theta l ij. This can be done so, and once you have this gradient, you can do gradient descent just like theta ijl value can be iterated just the way it is done in assignment number 7 minus dou j by dou theta ij l. Okay, which is this part. Okay, this will come here, and here you will have one additional factor which is lambda by m theta l ij, and this can be done completely vectorially. Okay, you can do complete matrix subtractions. You can calculate gradient in a matrix form, and then subtract complete theta matrices from the gradient matrices and get the new theta matrices. Okay, and the same thing was done in assignment number 7. Let's go back to there, go back to assignment 7. Still to open, let me try opening this. Let it open, and I will show you exactly the regularization portion where this was implemented in assignment number 7. Many of you have already solved it and commented it and have submitted. Hopefully you have got it correct. I have given it as an assignment even before discussing, because I thought it is a straight derivative from the straight intuitive derivative from the logistic regression discussion, the regularization of logistic regression discussion. So that's why I have not. So now I'm discussing it more formally here. So here, if we look at this iteration zone, you can see this is the this portion is the error function. Okay, so let me put back my. Okay, so this function is the error function. So you can see the error function until this point, which is the normal error function calculation. After that, we have lambda by 2m. And, a1 is the number of elements in number of rows. Lambda by 2m multiplied by square of all the elements in theta 1 matrix and sum, plus lambda 2 divided by 2m multiplied by square of all the elements in theta 2 matrix. Okay, so this is the new error function. Now while doing gradient descent, you can see in this place we first did the normal gradient calculation using the concept using the methods of back propagation discussed in lecture number 15. Okay, so this line, if you see, this one was all done is this one is normal gradient descent theta 2 gradient calculation. No, sorry, this line here is the normal gradient descent. After getting the normal gradient descent value, we add the gradient which is caused due to the regularization term, which will be what? Which will be you take the theta 2 matrix, okay, and it's simply the concatenation. So what I've done is simply concatenated the theta 2 matrix, okay, and have multiplied with lambda. So this is what it is doing is I am calculating this portion, okay, lambda into theta matrix, and I am adding it to the original gradient. This gradient was already calculated in the line 1. This is the line 2 after that, lambda into theta matrix, okay, and that is what is implemented here. So this is the first, the gradient was calculated using backpropagation. After that, lambda into the lambda multiplied by the gradient calculated from the backpropagation, sorry, from the regularization. The divided by m portion is not here, it is implemented here, okay, for both theta 2 gradient and theta 1 gradient. Divide by m has to be done for the whole gradient, so it is done separately here, okay, for both lines. Same thing has been repeated for theta 1 theta 2 matrix, and the same has again been repeated for theta 1 matrix. These have been compressed completely into just two lines by doing vector or matrix multiplications, okay. You have to think, if you think closely, you will be able to see how the matrix multiplications have um, completely eliminated a lot of loop operations which might have been which would have been otherwise required, okay. But overall, this is the implementation of regularization in neural networks, okay. So thank you for now. I will come back again with another lecture very soon. Thank you.